I'm going to talk about cloud infrastructure security. And this is where I come from. So this is a red team exercise that we did at a large financial institution. I think it's like 10 years ago, something like that. And I think it's interesting in the sense that it's a very typical, on-premises attack. So you start by compromising some web server in the DMZ. You find some kind of dependencies and you jump to like an internal segment somewhere. And there you find some kind of, way into the actual domain and the domain network where you have the like main Active Directory and everything. From there, maybe you jump to the next domain with some like cross-domain dependencies, whatever, and eventually you end up at your, H-value target, which could be like a mainframe if it's a bank. So that's a very like typical on-premises attack. So the question we're going to try to answer here today is, what would that kind of attack look like if they have the infrastructure in the cloud? So we're going to try to draw that kind of drawing that we had there in the beginning, but the cloud version of it. And we start with a challenge that there is no cloud. So what are we going to talk about even? But jokes aside, of course, there is a cloud. There's a cloud in the sense of there's APIs, there are these platforms where you manage your services, and people have the same kind of services, and it's like a common platform that we can talk about, and that's what we mean when we say cloud in this presentation anyways. So we're going to talk about today, so as was mentioned in the introduction, I'm a forensic investigator nowadays, so I do forensic investigations, and these are pictures from real incidents, and that's why they're anonymized, obviously. This is not one attack from beginning to end, like a real attack, but it's like all the components of the attack are taken from real incidents. But I put different ones together just because it would be very easy to de-anonymize it otherwise. But anyways, so this whole thing starts with this single-factor logon. And that's not good, right? You shouldn't have a single-factor logon exposed. But yeah, that's an explanation. And the customer says that, this device is enrolled and it's in the EDR. So this all should be fine. It should be isolated to the cloud. So we just changed the password. Well, they didn't say that, but we can see that they changed the password. And when we ask them what they've done, they like enforced MFA, you need to revoke the tokens, you need to like maybe reinstall the PC just to be safe, whatever. So case closed then, I guess. Well, the favorite thing we have as investigators is timestamps. So if you put timestamps on these things that we saw, the story is something different. So it didn't start with that the device was enrolled and then the password was reset, which would be most natural, right? It was rather the other way around. So the password of the account was reset, then the device was enrolled. And then we see the single-factor logon. So this tells a different story, right? And we also have a addition to the security information, which we didn't show a picture of. But that is something that is, I think it's an underrated persistence technique when it's like, you have this self-service password reset functionality, right? If you have an account, you can add some additional factors, and depending on the configuration, you can then reset the password. And that's maybe something that they don't check when they just change the password if they don't do a thorough investigation. So then you have like a backup way into the account whenever you want to as a threat actor. But let's look into that password change, because that's the thing where everything started, right? So we see that the account that did the password reset, it's one account that was resetted, or whatever that English word is. And then you have another one, which is the resetter. And the resetter is the sync_ account. And that points us to a hybrid setup. So there are three main types of a hybrid cloud that you use, which is federated, pass-through, and password hash sync. And to understand what type of attacks you can do, we kind of need to understand how these three variants work. So if we start with federation, that is typically like an ADFS, but there's other solutions you can use as well. The user goes to a federated app, and they say that they want access, and they say, no, you need to go to Azure Active Directory, which is, by the way, nowadays called Entra ID, but they keep changing names all the time, so I'm just confused, and I'm going to mix them up still. So they go to Entra ID, And enter ID says, no, you cannot go to me, you need to go to ADFS. So the user then goes to the ADFS server, and the ADFS server checks with Active Directory. And Active Directory validates and checks everything, so everything is good and fine. And then they give them a token that is signed by the ADFS server. And that step is kind of important here. So the ADFS server signs a token with secrets that is stored on the ADFS server and says, well, you know, if you have that token, you can give that to Enter ID, and they can validate that because they see that, yeah, this is signed by the actual ADFS server. So then they give them a specific token, and then they can present that to the federated app. And eventually, they're in and can do whatever they wanted to do in the app in the first place. So what we saw here was like this chain of trust, right? So the federated app trusts Enter ID trusts the ADFS server, and the ADFS server trusts Active Directory. So what happens if someone compromises the ADFS server? Well, then they can steal that token and the signing token certificate and the distribute the key manager, blah, blah, blah secrets. And that's what they did if you read about the SolarWinds attack. This is exactly the kind of attack that they did at that point, which is called a golden SAML attack. That is super cool and everything, but that doesn't really involve a password reset, right? So that's not really what we're looking at here. There's no password reset needed because you would just be authenticated all of a sudden because the threat actor is your ADFS server at this point. So let's go to pass-through authentication instead. And in that case, the user goes directly to Enter ID. They ask who they are. They give them the username password, and that is put on a logon queue. And then the Connect server, which is something that is installed on a server in the customer's environment, checks for new logons. And then it gets the new one on the queue, and the queue validates that against the Active Directory, which then pushes it to Enter ID. And this step, it just gives a Boolean which says that, yes, those are valid credentials. So then the Enter ID can let the user in and do what they wanted to do. So same thing here then. What if the AD Connect server is compromised? Then there is this technique called skeleton key, which is that you patch the function that validates the login and gives a true or false as a response. And you can change it to, you know, if the password is banana and username I don't care about, then let the user in. And then you have the the skeleton key banana, which you can use to log into every single account in the entire environment. That is implemented in AAD internals, which is a toolkit which I recommend you to look into if you want to learn more about Azure security. And still, this is not a password reset, so let's move on to the first one, to the last one. And in this case, it actually starts with the AD Connect server. So in this case, the AD Connect server asks the domain controller to give me all the passwords because I need them. That is a typical password hash sync kind of thing. Maybe you've done that as a red teamer somehow in a bad sense. This is what it's actually supposed to be used, the real use case. So they get all the hashes, and then it actually hashes them one more time because they don't like NTLM in Azure, so they actually have a new hash, which means if you dump hashes in Azure, you're actually not going to get the classic NTLM, the NTLM thingy that you're used to see when dumping hashes in on-prem AD. So you're going to get this kind of hash instead. But anyway, so the point here is that they sync the hashes and they keep them updated all the time, which means that Entra can all by itself decide if your password and username is legitimate or not. And at that point, there is no need for a connection in between. You just need that sync. So to make all of this work, you need a bunch of secrets, right? So you need one secret, which is the MSOL account. If you work in a SOC, you might have seen alerts about that account syncing hashes. That is usually a false positive, but if you see that from the wrong server, then it's usually not a false positive, and you need to act on it very quickly because it's really bad. But it's a very common false positive, right? Because that's like an account that syncs password. And then you have a service account, which is running the actual service. And you have the sync account, which is talking to Azure and is actually, creating new accounts and changing passwords and doing all of that. The service account is interesting because that's the context where this service is running. And these secrets, the passwords to these two accounts, are stored with TP API, which is a encryption, like a reversible encryption in Windows. And if you're running in the same context, you can just call protect or unprotect. So you can just get the password as is. And If you imagine that the threat actor are on that server and they have compromised that, they can get the username and password to that sync account. And that sync account obviously have the permissions to do the password reset that we saw. So that's interesting. And when we look in EDR, we see that that is exactly what they did. So they read out those secrets from the AD Connect server. And you see that this is the actual account. And when we look closer into this alert, we see that this originates from the wrong IP address. So the real password sync, not password, the real sync is going from the legitimate server while this happened from another server. So that's another quite strong indication that this is something is not right here. So if we look closely into this account, we see that it's a built-in account in Azure, or rather it's uses a built-in privilege role, which is called directory synchronization accounts. Since I wrote this presentation, this has actually changed. Speaking of that, they change things all the time. So the specific technique that we talk about is not going to work. And I think it did work when I wrote the presentation, but now they changed things pretty recently. And this is typical when we talk about cloud security. It's like a moving target all the time. And this, like, minute you feel like you actually learned something, it's already changed. So it's kind of horrible to work with, but it's also like good for us as defenders, and it's bad for us as defenders because things can become vulnerable that wasn't vulnerable yesterday, and vulnerabilities can just, there's no CVEs for cloud, for example. Like they will just, if you find a critical vulnerability in Azure, report it to Microsoft, they will give you credit in online services. There's no CVE, like you have no idea what vulnerabilities there were or not. But anyways, so this is a very highly privileged account. And this is kind of interesting because it's not global admin, but the threat actor wants to be global admin. So how could they take this account that they have a password to and escalate the privileges to global admin? How does privilege escalation work in Azure? This is a really good example of that, I think, because this one has two privileges which are interesting, which is the take ownership of an enterprise application and change service principles for it. So basically, when they have this account, they can take a look at what enterprise applications there are in this organization. And in this case, there was this backup application, which has really high privileges because it needs to take backups from everyone's data, and it needs to do a bunch of stuff to be able to be a backup application. And one of those interesting permissions that it had was the read-write directory permission. And since the threat actor is able to take ownership of the application, they now can act on behalf of that application, and then they can exercise those additional privileges, which means that they can use those privileges to make themselves global admin. So it's quite a simple escalation here, right? And this becomes much more difficult when you start looking into the RBAC model and everything that is in Azure, and it's really complex in a large organization to not have these escalation chains. That step there where they acted on behalf or like as the application is kind of interesting also in a persistence sense, because as investigators we tend to, we know this bad thing happened, let's see if there was any new applications registered, but you should also check if someone changed existing applications, because you don't need to create a new application if you can just add your principal to an existing application, which means that you have an API key basically to act on behalf of that application. And that is something that is really hard to find actually if those default 90 days or whatever log retention period you have has gone out. Because you have this log entry which says that they added a service principal credential, but after that period it's kind of hard to get that out. There's no like easy way in the GUI anyways. So they added themselves a global admin and they did all of this, right? The thing that is a bit weird still, I guess, is that this device was in the EDR, right? So how that doesn't make sense, because the threat actor enrolled their own device and then logged in with single factor. And it turns out that this customer when you enroll your device, they automatically push out an EDR agent. The threat actor did not know that. So the customer came to us and said that, I think we have a full export of the threat actor's machine. Do you want it? It's like, yeah, sure. So, yeah, that kind of backfired on the threat actor, I guess. They tried to be stealthy by being enrolled and, making no alerts, but yeah, that didn't really work out. We'll get back to that. If we draw this, like we did with the previous thing, we see the first thing that we know at this point is that they are on the AD Connect server. They dump secrets there, and then they take over an enterprise application. They make themselves global admin, and then they enroll the device, and they add some security information for extra persistence, and then they do exfiltration from high-value targets. So that's like the final goal of this campaign. We haven't really shown any pictures of that because it's just a bunch of logs of downloads, which isn't that fun to look at, maybe. So the question is, like, how did they get to the AD Connect server? Because they can just show up there out of thin air, right? They need to somehow connect to it. And we see traces back to a local Jenkins server. And Jenkins is this build server that is quite commonly used. I think it's more commonly used in the customers that tend to get incidents than customers that are really like on the forefront. In that sense, like, it's not a bad solution per se, but I think a lot of customers are really like built into Jenkins because they've invested a lot in like plugins to Jenkins, and they have this like really big Jenkins server that kind of builds everything. At least that's the case with this customer here. So Jenkins isn't bad by itself, but it's usually used in a bad way. So for example, if you have the administer account, there is a built-in remote code execution. That's a feature which they like clearly specify. You can execute code on the underlying system from the web services. So that's not so good. It's also quite easy to just dump all the secrets. You can imagine if you have one Jenkins server that is supposed to build to production, test to whatever and whatever, and sync from this repo and add container images to this registry. Like, it needs all those secrets. And if you just run a script like this, you get all those secrets. And that is what we found that they did. So they got like a lot of secrets because, you have this one big Jenkins server which has the secrets to everything. And the next question is, like, how did they control the Jenkins server then? So we found that there was a rat running on the Jenkins server, and it connected out to Gmail, which is kind of interesting. And this is a case where threat actors also use the cloud. And I call it C2 as a service. I don't know if that's a name that's going to catch on, but basically, it doesn't have to be Gmail. This can be, like, we've seen it with Dropbox, we've seen it with S3, we've seen it with Slack. Like, pretty much any service you can use this, where you have the possibility to post a message and read a message. That's pretty much everything you need. So the way it works is kind of that, you create a draft in Gmail. You don't have to actually send a mail. You create a draft, and on the other side, the threat actor is logged on to the same Gmail account, and they read the draft. And then you sync data that way back and forth, which means that you can create a C2 channel over that protocol. And this is kind of smart because what we're going to see soon is that this customer actually used Google Cloud as their development environment, which means that a lot of traffic is going to go through Gmail, or at least like Google servers, with like GCP and so on. If it's a smart threat actor, they pick something that you use. If it's a stupid threat actor, they pick like Dropbox at a bank. And that's super forbidden, and they have really good detection for that. Not for security, but for GDPR and things like that. So it can also stick out a lot. But if they look at what is actually legitimately used in this customer, and then they pick that, then it's actually really hard to see this, at least from a network perspective. And obviously from the other side, we're completely blind because we're not Google. So we cannot see what the threat actor do towards them in Google. But if we reverse the malware, we're actually going to find some kind of API secret, right? Because it needs to authenticate to that. And if it's persistent, it needs to keep that somehow within the malware. And there are different philosophies here, but I'm a quite strong believer that it's a really bad idea to use that API secret to log on to the account. Because we can't do that, right? Technically speaking. But keep in mind that if you find a secret like this, and that goes for SSH servers and whatever else, and I see a lot of people just going complete cowboy and hacking the hacker. But keep in mind that the Gmail account is probably not the threat actor's account. They probably hacked that account. So you're probably hacking a third party, and you're just a second hacker hacking that account. And there's so many things, like in a while FBI is going to find that account, and it's going to be quite hard to explain for you what your IP is doing in that account. Maybe you're using a VPN or whatever, but it's really a bad idea. Plus, I don't know the law in Germany, but in Sweden it's also illegal, so it's stupid for many reasons. So don't do that. Instead, what we have good experience with is going through communities like First and TFC Cert and other like trusted vendor communities, and then just talking to the people at, for example, Slack or at Dropbox. Because they really hate it when people, misuse their infrastructure as a C2 channel. So they will usually be really helpful. Plus, they can actually, track down the entire threat actor infrastructure, because they can look from a broader perspective than you can when you try to use some API key. So it's just much more effective, and it's just like the good way to go. So strongly recommend doing that instead. But anyways, so how did I get to the Jenkins server? We see that there's a malware on the Jenkins server, but that doesn't explain how the malware got on the Jenkins server. So let's go into that. The Jenkins server in this case is configured to run Docker containers with build jobs. And it's just like this one big Jenkins server, everything runs on the same machine. And we see that the logons to the Jenkins console comes from one of those containers. And the reason that that works is that because someone figured out that these containers need internet access, so they need, fetch dependencies and whatever. So they put them on the default Docker network, which means that you can also reach localhost on the host, and yeah, there you go. You can log into the Jenkins console. So the question is though, how do those containers get compromised? Because it's not like they're internet exposed. It's just like offline build jobs. So we've seen a few different scenarios of how that can happen. And one of them looked like this. So you see that this is a package which has version 9999999 something. And the name of this package is the name of an internal Python package at the customer. So company name library dot whatever. And if you look in the official PyPy repo, you see that someone has registered the same name. And they put a version 99999. And the thing here is that if you use extra index URL to point to your internal PyPy repo, then pip is going to just select the newest version from the public or your internal. So what they say is that you need to use index URL instead if you want to only use your internal repo. Otherwise, this is an expected behavior. But no one have the time and interest to sync the entire PyPy repo and keep all dependencies up to date. So people still use extra index URL, unfortunately. And this is just a closed non-fix. So it keeps happening time to time. It's called dependency confusion, and there's a good write-up there from that guy there if you want to read more about it. Another one we've seen is kind of interesting. It's a feature in pip, which is not a feature, but it's a bug in pip, but it's not a vulnerability in pip, according to there's no CV for it. And the thing is, if you have an extra index URL configured, it would make a clear text request, the first request, and then it would upgrade to SSL. So we basically saw a man in the middle, which just responded their own package instead of the real package. Another way that could happen is if someone compromises the code repository, right? So if you have this GitLab CI something, you can change what runs in the container. You can also change the actual code, right, that is going to run in the container if you can push to the repos that's going to run there. This is all in itself a really big topic. We have the problems of shared runners in general, where you have usually you protect your branches maybe, and just not everyone can push that's going to run on the build server. Because you have the problems, right, where you can dump the environment secrets and everything like that. If you're able to change the code that's going to run. But if someone is able to create another Git repo and that's going to run on the same server, then eventually they can just start their build job, and then you can just stick around there and wait for the sensitive secrets to pop up. What we saw in this case was that the threat actor compromised a GitLab account. And we see that they made a push to the repo, and they changed the requirements.txt file. and they changed the name of one of the dependencies to GitHub and the name of the dependency, which is a threat actor-controlled GitHub repository. And if we look into that and we do a diff from the legitimate package to this bad package, we see that there is one file that is changed, which is a setup.py file, and that's something that's only going to run when you install the package, which is exactly what happens in this build environment, right? So it doesn't really affect the production or anything, it just affects this build stage. So we see that they come from GitLab, basically, and that also connected out to the C2 channel from that compromised container, which then used the network to break out to the underlying Jenkins server. And from there, found a bunch of secrets. We were able to jump to the internal ID Connect server, which made it possible to then jump into the Azure environment. So the next question is then, because we know that they execute code in the container, right? But that doesn't mean that they can just get the one of the administrator accounts in the Jenkins interface, right? That's another set of credentials that shouldn't be in a Docker container. And the answer here is kind of long, because it starts with GCP and how lateral movement works in GCP. So imagine that you're a threat actor and you compromised one machine in Google Cloud Platform, GCP. So, this is kind of interesting in the sense that if we go back to what we were talking about in the beginning, in Windows Active Directory, like where I come from at least, and the classic on-premises attacks, like in pretty much every single attack, you have that the threat actor compromises one machine, and there is some kind of dependency from that machine to the next machine. That can be like they reuse the local admin password. It can be that a admin which has higher privileges, like a domain admin, for example, uses RDP to log on, and then their credentials are cached in memory, and they can dump that memory and then log on to the next machine. There's a bunch of different, you have like service principals with that credentials are stored in LSA and so on and so on. Point is, this is like classic on-premises lateral movement. And what we're going to see now is like, what does that look like when we're talking about Google Cloud? And there's kind of an interesting default setting in Google when you create a virtual machine, which is that by default, you will have a service account running as the machine, which is going to be stored on the machine. And the default setting is that it has like read access to storage and stuff, which is like a really high privilege as default. And you can like curl the metadata, for example, to get this out. This is something you might have seen if you're into web application hacking. We can do SSRF in the cloud, and you can dump the metadata for the machine that you're executing on. I think they changed that quite recently. Nowadays, you need to also specify like a header, so it's a bit harder to get it out now with the SSRF. But now we're talking about a threat actor that has compromised the machine, right? So they can obviously get all of this. So that's one way to get that default service account. Another way would be to get cloud CLI secrets, because in environments where they have like a pretty good, they've locked down the environment with VPCs and things like that, then you kind of need to jump to a machine and from there access the APIs to troubleshoot something and so on. We have this infrastructure as code, but in practice, it usually requires quite a lot of manual magic to make things actually work, right? So what the threat actor finds in those cases is that someone SSH, a legitimate admin, SSH to a machine, and from there they want to use the CLI tool. So they do gcloud init or whatever, and then they authenticate the session, and then that sticks around in your user profile. So if they're admin, they can just dump those stored secrets, and then they're inside your gcloud. So it's kind of easy to get that. You can probably decrypt things and do it like in a really fancy way, but the easiest way is just copy this folder and paste it in your own machine, and it's just going to work. So if you start using these admin tools and you spread your admin presence on a bunch of systems, then the threat actor is going to be able to get them when they're compromise the machine. So basically, that's what the threat actor do. They look at what kind of secrets are stored here. It can be this kind of credentials that we're talking about now, but it can also be the password to a SQL whatever, because the application needs access in a connection string. It's a bunch of different things. We try to jump to the next machine. And in this case, they find a counter that has like set instance metadata. That's kind of how it works in Google. Like you add your SSH key and when you run the SSH command. And that will look something like this when you do that. And then they log on to the next machine. And of course, they just repeat the process. So maybe they didn't get everything they wanted in the first machine. That doesn't, happen often. But when they start doing this iteratively and very methodically and just searching for new and new and new credentials, eventually they have access to what they want to have to. So this is kind of interesting in the sense that this is very much the same as we see in on-premises Active Directory, right? It's not that Active Directory is... Sorry? How many more slides do you have? Oh, yeah, it's soon done. Sorry. Completely lost time here. Okay, so basically it just keeps going like that. And in this case, we see that they dumped the credentials that they needed to execute code on Jenkins to log in there from this escalation in Google Cloud. So the question we're going to answer now is like, how did they get into GitLab? And there's a bunch of ways to do that, bypass MFA. One of them is info stealers, because it's quite well spread, these info stealers. You see them all over the place. They focus on like browser secrets, a bunch of other things as well. But when we talk about GitLab and so on, that's the interesting part, right? So it's kind of easy to dump secrets. This is pretty much a one-liner to do it. Just start Chrome, connect with the debugger endpoint and get the cookies. You have other types of secrets as well. If your account is Azure Active Directory joined, you can dump the refresh token and so on. We start to get a bit better when it comes to this. We start to have some kind of token detection and so on if tokens are stolen. But there you have pretty much the full attack, right? So it starts with a info stealer on a client. They use that to jump into the GitLab, execute code, and then they're able to jump to a machine in Google Cloud, escalate, and then you have the full attack from there. We also have a strong indication in this specific case because we, had EDR on the threat actors' machines. So we can see them browsing Russian market, which is a market for that kind of thing. And the original source and the final thing we're going to talk about today is the source of that Redline stealer, which was hosted on the Microsoft's official GitHub account, which is kind of weird. And their competitors were really quick to point this out. But Bleeping Computer did some digging and figured out that this is not hosted there. Well, technically it is, but it's not that the repo is compromised. It's actually a feature in GitHub, which is that if you answer a issue and start just doing a draft, you can upload a file as part of that answer. And if you just discard this, the file is going to be hosted. And that answer is going to be under the repo. So the last time I checked anyways, this was still possible to do. So it's quite an interesting feature that they have. And with that, I want to thank GitHub for hosting my slides in their official documentations. And by the way, this link doesn't actually work. You don't need to... it's 1234, 1234. The vulnerability is there, but it's not a real vulnerability. So it's not... I actually didn't exploit it. My legal didn't think it was a good idea. But yeah, so cool. Sorry for running over, but thank you very much.